And now we're going to have frontier perspectives. What that means is that some of our best and brightest are going to give us a short glimpse into what they do and the projects that they run. It's called Frontier Perspectives AI Interacting with the Physical World, because it's not all just in cyberspace. There's physical robots doing things, and I think we need to be cognizant of that fact. There'll be 4 gentlemen speaking about this, and the first one is Václav Kubáček, the researcher from here, CIIRC CTU, talking about humanoid robotics, beyond the hype, challenges of sim-to-real transfer. And I think beyond the hype is a very important sentence to be said out loud these days. Please, round of applause. Thank you very much.
Yeah, so about sim-to-real gap, mostly in perspective of humanoid robotics. I would like to divide it into 3 levels, to have better simulation and better physics in simulation, abstracting reality through domain randomization, and gathering large amount of training data. These decide whether humanoid robotics will remain in impressive videos and demos on the internet, or move beyond them towards reliable use cases. Reflecting our past in RICAIP, we gained great and extensive experiences at simulation, extensive robotic automation cells, creating digital twins, doing virtual commissioning. Basically, we are all the time doing the sim-to-real gap in industrial use cases. But we would like to move forward and meet the next major technological frontier, and then that is the humanoid robotics. For that purpose, we established the Interdisciplinary Center of Humanoid Robotics, and our mission is to develop and deploy practical and safe real-world use cases and bring humanoids into human-changing environments. Traditionally, we program industrial robots with control theory by solving kinematics equations. But now we are in the era of physical AI. In simulators, we let robots to learn themselves by trial and error. But simulators or simulations by definition cannot be perfect. They rely on rigid bodies, instant actuators actions, and uniform friction. But the real world is harsh. There are introduced noises, the links and joints flexes, and the actuators heat up. And those accumulative failures, or those accumulative small mismatches, leads to policy to fail. And the long-term goal in this area is the zero-shot transfer, to be able to simulate the robots in simulations and transfer to real world without any fine-tuning. So we still have to start at the simulator and how to better simulate physics in it. I hope most of you are familiar with Mujoko, which is a gold standard in the robotics community. And next we have Isaac Sim, which gives us scalability in terms of reinforcement learning by computing thousands of environments on GPUs. Now let me introduce Newton physics, which brings idea of multi-solver physical stack. The important idea is to use a specified solver for the right phenomenon. From solvers for contact-rich learning, through complex parallel joints without numerical instabilities, to specialized deformable solvers for soft structures, non-rigid bodies, clothings, or hanging cables. And in humanoids, all of them combines. But to actually simulate the reality into every atom, it's impossible. Rather, we can use the simulator and great advantage of it, and that's the scalability, and actually deliberately interrupt or disturb the scenes and also the robotic models. We can introduce randomization, randomized friction, textures of the surfaces, motor performances, or masses of each joint's length, and even we can perturb robot with external torques, where the uniform domain randomization may be clumsy, because if the randomization is too wide, it leads to conservative, scary policy, and robots are slow. And if it would be too narrow, then the policy is very fragile and fails on concrete. To fix this, we can introduce active domain randomization. It sets up a two-player game with the policy that's learning and how to move the robot in the controlled environment, and the second, the adversary that actively pushes the limits of the learning environment. It ensures to achieve optimal learning rate. It's just like the humans. If the environment is too easy, we'll learn nothing, and if it's too hard, then the policy output is random, and the robot learns nothing as well. So by this, we can achieve better generalization of policies. Another great problem in sim-to-real gap is the gathering large amount of data. For years, we have been dependent on teleoperation. Humans with VR goggles operating the physical robots and through tasks. And it is both expensive of human resources and the robot machine time, and so it's unscalable. The innovative approach is to completely remove the physical robots of the data gathering loop. Basically, we can treat humans and humans doing a task as the most scalable source of data we have on the Earth. At ego scale, they use the visual SLAM and hand pose recognition, and from then that extracting manipulation trajectories and retarget them directly on robotic arms. Then the robot teleoperation shall be used mainly for embodiment alignment and fine-tuning for specific tasks. And this leads us to the next generation of simulation, and that's actually generative world models, which are generating virtual training environments. Common text to video diffusion models cares about how the video is pretty, but the Cosmos cares about the physics and how accurate it is. It can create plausible futures, task variation, and robot-relevant visual dynamics. Cosmos focuses on physically meaningful video, where gravity, collision, and spatial structures are accurate, and by robots interacting in it, predicting the future frames. This virtual world gives us infinite number of training environments, and we can train VLA models like Isaac Groot. So there is great synergy where Cosmos virtual world generates scenarios, and Groot learns in it, validates, and learns. Together, they point towards scalable, humanoid, zero-shot deployment. And to conclude that, there are still many challenges to solve, but the rapid evolution of physical AI makes them totally achievable. Thank you very much.
Thank you so much. And also congratulations on your new center. That's awesome. Yeah, celebrating young talent. Thank you very much. And also goodbye to Antonio. We will You will be missed. Thank you for all your contributions today. Thank you. Thank you so much. Right, the next person to speak to us will be on the theme of modeling the world and objects in 3D, and is Torsten Sattler, the senior researcher here at CIIRC CTU. Again, the floor is yours. Welcome. Thank you. Yes, please. Yes, yes, yes.
Well, let's see whether you're still applauding in 10 minutes. I'm Torsten Sattler. I'm one of the 4 tenure trackers hired as part of the RICAIP project. I think I'm the only one talking today. I guess part of RICAIP, I came to Prague to build my own research lab. And one of the things that we're doing is trying to build 3D models of scenes and objects. And that's what I want to talk about now. And we're interested in building this from images. So our input is a set of images, and then we typically do 2 stages. The first tries to estimate where all of these images were taken using something called structure for motion. The output is what you see here, like each red pyramid corresponds to the position and orientation from which an image was taken, and we get a sparse reconstruction of the scene geometry. And in the second stage, we try to build a dense, detailed 3D model. For example, what you see here, this is about 4,000 images captured in the city center of Aachen, where I did my PhD. And this dense reconstruction approach is done using machine learning. More precisely, we follow an approach that's called Gaussian splatting, where the idea is I represent my scene through thousands or millions of small objects called 3D Gaussians, which are defined by a position, a spatial extent, it's essentially ellipses, and a view-dependent color function. View-dependent means that if you look at a surface from different angles, you get potentially different colors, allowing you to model reflections and refractions. And the nice thing is that you can render these things very efficiently, especially compared to prior methods, by essentially doing what GPUs were designed for like 20 years ago, which is rasterization of objects. And this is the output of this algorithm. This is not a video, but it's showing a fly-through through a 3D reconstruction. This is really reconstructed from images. So you can see that you can get actually a photorealistic reconstruction. But as anything with AI, it's strongly, like depending on how your input data is, the output quality will be. So what you see here is actually zooming in and out of this reconstruction. And you notice that the spikes, for example, of these wheels are way, way too thin. What is happening there is that we are modeling objects by these 3D Gaussians. When we render them, we end up with a 2D Gaussian, and the whole learning algorithm tends to generate millions or lots of many small Gaussians because you want to model fine details. As with everything, a lot of objects typically make the learning process hard. You run into numerical optimization issues. And what the original paper published in 2023 did is they made sure that each Gaussian would render to at least a pixel by dilating the 2D Gaussian, which makes the training process robust, but introduces all these artifacts that you saw before, which is if you zoom out, everything looks larger than it should be because you dilate it to a pixel size that should be smaller. And if you zoom in, you see these very tiny objects, which come from the fact that this dilation operation allows you to generate like very thin Gaussians, but you still reconstruct the training images perfectly because you dilate them to the right size. In 2024, we showed that there's luckily a very, very simple solution to this, which is we have small Gaussians, which is lots of high-frequency details, and there's a very principled solution to handling with problems caused by high-frequency details, which is a low-pass filtering. So we enforce that 3D Gaussians have a certain minimal size, and then do smoothing in 2D to handle artifacts. And here you see the original formulation on the right, and here ours on the left. And if you zoom in, you see that our spikes are large, have the right size. They render to the right, to the right thickness. We presented this in 2024. Won a best student paper with it at one of the major computer vision conferences. which is always a bit of a luck factor. And most of the code that we created is public. As the previous speaker mentioned, one of the things that you could use this technique for is creating virtual worlds where you then can train robots. And for these virtual worlds, you would like to not only have control over the viewpoint, but also over the conditions under which you observe this. So this is Trevi Fountain in Rome, trained from images taken under different conditions, day and night. So we developed an approach that would actually allow us to handle this type of changes. And it allows us to not only change viewpoint in the scene, but also change illumination conditions. And we get a very smooth interpolation. So here you see two conditions, and we smoothly interpolate them and apply the lighting, resulting lighting on the model, and you see that it smoothly varies from day to night, different illumination conditions. But this required us that we would actually have data of the scene taken under, say, a day, a night, and so on and so on. And one question that what we're currently looking at is how can you simulate different conditions if you actually don't have the data. So, for example, if you would have only taken images in Halloween night, could you simulate how the scene would look like in summer and day or in winter at night? And one of the things that we're looking for is actually using generative AI to simulate these different conditions. And here's a very sneak peek of the results. It looks largely horrible, but what you see here, what we're actually caring for is the background and what's on the ground. And that is remarkably consistent, actually, given that you are applying a diffusion model on each image individually. It will hallucinate geometry, it will hallucinate details that are not consistent with other images. And then you're running it into a method that is expecting multi-view consistent images. And we're currently ironing out the kinks, and I hope we will get a submission out of this later this year. The other question is, can we build 3 models that are actually useful beyond displaying or beyond simulation? And in a different line of work, we looked into using these 3 reconstruction techniques for object manipulation for robots. So in this case, we would scan different objects, would reconstruct them. So what you see here is a reconstruction, and then use these reconstructed objects rather than ground truth CAD models for object pose estimation. So the question was, can we actually go beyond having to have very, very precise scans of different objects that the robot could then identify and estimate their pose and ultimately manipulate, and do this only from images. And this is the result. So these are different reconstruction techniques for 2 different ways to estimate the object pose. So given an image, we try to determine for each object from which position and orientation, where it's positioned in the scene, what the orientation is. And here you see so higher numbers are better, measures accuracy of the pose estimate. And this is what you get with the ground truth, like very detailed laser scan for the 2 different pose estimation methods. And you see that with very good reconstruction approaches, we are actually able to get relatively close compared to having, like, say, a half an hour 3D scan of the object. And in recent work that Varun Burde, who is Pavel's and my PhD student, is going to present at ICRA, I think today, we looked into whether we can actually also use these 3 models for object manipulation. So given a reconstruction, which is the red model, can we determine where to grasp the object and then grasp it in simulation? And yeah, that's an overview of what we are doing. If you have any questions, feel free to ask. Otherwise, thank you very much.
Thank you so much. When I saw the Fontana di Trevi, that was very, very encouraging. I have some archaeologists who might want to talk to you, myself included.
Happy to.
Yeah, so this is great, and it's amazing to see like how widely you can use this type of technology, from digital twins of factories to reconstructing heritage. So thank you very much.
Thank you very much.
Thank you. Amazing work. We're very happy to have you. Thank you. So, ladies and gentlemen, that's 2 out of 4. Let me use this opportunity to say that afterwards we will have tours of the test bed. Depending on how many people want to go, we will be going in kind of directions against each other, like Napoleonic armies. So there'll be one coming this way, one going that way. That'll be at 4:45 after the coffee break and after the final strategic roundtable. Before that, however, I would like to invite Vladimír Petrík, a researcher here again at CIIRC CTU, talking about embodied AI. Please come and welcome and come join us on the stage. Thank you. The floor is yours, as is the microphone.
So, thank you. I will talk about embodied AI. And let me oversell for a second. In the digital world, AI is basically solved. It understands your images, can reason about the physics which is shown in the image, and it will drive your computer to get the things done. We saw some results already today. It's extraordinary and it's already everywhere. And now we are putting the same intelligence on the robot. With vision language action models, the robot observes the scenes, reason about the command you give it in natural language, and executes the actions. These are kind of impressive results you can find online. A robot can cut an apple or do your laundry. But AI isn't perfect. There are always mistakes and misunderstandings we can't fully get rid of. In the digital world, a mistake is click of undo. In the physical world, it's different. Mistake is either hard to recover, like this pudding example here, or it's dangerous to humans surrounding the robot. And the physical world has no undo button. So the real question is not whether we can achieve impressive results, but whether we can trust them to act correctly before we let them into your homes or factories. And that's a validation problem. And to tackle that, we started with simulation. We built a benchmark called Realm, where you can run thousands of trials safely overnight. It's real-to-sim validated, so we can trust the results. And Realm shows us where a policy breaks. We change the lighting, add distractors, or rephrase the instruction. So instead of pick up the banana, we say pick up the yellow object. And the results are sobering. Today's best policies achieve only in 60% of times. But not everything can be simulated reliably or fast enough. So can we use a data-driven simulator instead? That's the word model, as we saw already. More concretely, these are action condition word models. You give them an initial observation and a sequence of actions, and they generate the next multi-view observation autoregressively. Here is an example generated by Control Word from Stanford. It produces next looking visuals, effectively simulating what the robot would see. And all of it was learned from data. But due to their autoregressive nature, they fail on long horizon sequences. You can see it here in this pick and place example. The object gets deformed during manipulation, even though it's a solid Lego brick. So this is physically inconsistent. That's why we introduced Persis word, an RL-based algorithm that stabilizes word models over longer sequences. Our is shown here on the bottom, and watch the region in the red box. The baseline distorts the robot significantly, while our holds the structure in place. With this post-training, we keep the word together long enough to be useful for simulation. But our word is not only RGB. Our word is 3D, and the robot needs to understand it. So we designed depth word. It predicts 3D geometry using depth and point map, and allows the robot to reason about the geometry. Additionally, by predicting the depth, we also improve the quality of the RGB prediction itself. But both classical simulator and word model are still only proxies of the real world. In the end, we have to validate in the reality. So the community is building exactly this, real-world validation. It's called Robo Arena. Real arms in real laboratories run the same policies on the same tasks, and they are ranked by blind comparison. And CIIRC is part of this evaluation. We are one of the evaluation unit. So this is real physics. We can trust the results, but it comes at a cost. It's slow and expensive. And every single trial needs a human to set it up, watch it, and reset the scene. So real-world testing today doesn't scale. So the frontier, in my opinion, is making real-world testing scalable, with no human in the loop. The robot runs the whole cycle itself. It executes the task safely, records the outcome, reset the scene, and repeats. But safety is what unlocks this. We need robots that reason about forces and fail safely, so that they can run without the human. On the video here, you see a result, whole body compliance from MIT team, which lets the robot absorb an unexpected collision instead of breaking something. And once we achieve this for all robots, we can run them safely, and they can reset itself, and validation will finally scale. And I talk about robotics mostly, because that's where my expertise is. But robotics is just one instance of something bigger. The same physical AI loop applies to many different domains, including manufacturing, energy to control, and biotechnology. All these areas require AI in the loop, and a control layer, yet at different control frequencies, from milliseconds in robotics to days in biotechnology. And that's why CIIRC submitted a large research infrastructure proposal to create this infrastructure for physical AI that allows AI model to be validated and to interact them with the physical world. So to conclude, in my opinion, physical world is the next frontier. Thank you.
Thank you very much. Thank you. Before we go on to the last gentleman today, I think it's just worth recapping the talent that we're seeing here in these perspectives. We were discussing it in the morning blog, how important it is to keep these young, talented people here. And it would be great just to recap that Vlado is from the group of Josef Šimit, who's also an ERC Advanced grant beneficiary here at CIIRC. So it really is absolutely world-class research. And he also works on the Elliot project, which was mentioned here earlier. Torsten also is the RICAIP tenure track position holder and actually came here thanks to RICAIP as well. So you can see the concrete fruits of RICAIP as a project resulting in such wonderful talent that we can house here. And of course, we have the new research center on the humanoid robots that was presented to us by Václav Kubáček. So thank you very much for that. Last but not least, we have Matěj Sulitka, who will be talking about something we called the lower ground test bed, which sounds cryptic, and it is, but you'll have a chance to see it if you're brave enough. Please take it away. The floor is yours, and thank you for coming.
Thank you. Thank you for the introduction. Ladies and gentlemen, it's my great pleasure to give you some overview of activities we have been developing within the RICAIP project. And as mentioned, it's the activity of the so-called lower test bed. Actually, I will be talking about the use of digital twins in manufacturing and more concretely in machining operations. Still, machining is one of the key technologies, key production technologies we do not need to omit. And digital twins represent a new paradigm which may significantly help in improving the processes. What is the status nowadays? The manufacturing processes are planned using the standard CAD, CAM softwares, which provide us the toolpaths and the opportunity to define the cutting conditions, etc. However, still the great lack of the CAD, CAM softwares is that they do not have any information about the behavior of the machine tool and the process. Therefore, in many cases, we need to tune the process parameters directly on the machine and to do the iterative processes on the machine before we can launch the production to the reality and to have the outcomes of the machining operations which fulfill the requirements on accuracy and surface quality, of course also on the machining time. So as I have already introduced shortly, the new paradigm is brought by the digital twins. We have been focusing in our use case here on two different levels of the digital twin. The first one is being the predictive digital twin, which allows us to test the machining in completely virtual environment before we go to the machine and validate whether our toolpath, cutting conditions and whole setup of the machining operation fulfills the requirement on the results we want to achieve. Here I need to mention the digital twin actually is a concept which consists of three main parts. The first part is the physical object, in our case the machine tool. The second important part is the virtual model. And the third important component is the data transfer, and actually in both directions from the physical object to the virtual model and back from the virtual model to the physical object. The other level of the digital twin we have been testing is what we may call post-process digital twin based on edge data we can get directly on the machine. The difference in the scheme is here that the data according to which we run the virtual simulation are obtained directly on the machine from the linear scales, and we can get then theoretically on the machine directly the picture on the machining results without the need of taking the part, the measurement and back to the machine to get the results we want to have. So those are the two levels of digital twin we have been testing. Here I would like to give you a short glimpse also on the simulation tool we are developing for a long time at CTU, and actually which provides a very detailed analysis of the machine surface, both in terms of surface quality and machining errors. This is an important part of the whole concept of the digital twin, so that without this visualization actually it would be very difficult to assess the results of machining operations. And now already our use case in a RICAIP, one of typical machining operations at which the digital twin may provide the benefits in terms of evaluating the quality and accuracy of machine surface is the freeform machining represented by mold machining, and for those operations a key component in the whole chain starting from the CAD, CAM software preparation up to machining process is represented by the CNC controller system on the machine, which is responsible for possibly many errors occurring in machining, vice versa. Proper setup of the parameters in CNC control can save the machining results. We have been doing our study on a numeric controller which provides kind of specialized cycle 832, which allows the user to set the parameters of the process which leads to smoother path motion of the tool and a shorter cycle time. Now we will see a list of a few pictures illustrating the results which we have been capable of getting completely in a virtual environment. The first example here is the visualization of the distribution of real feed rate. You can see that there are significant differences between the both cases where the cycle 832 is either off or on. We are of course interested what are then the impacts of activating the cycle 832 on the surface errors. Again here we can see the comparison in both cases. Also with significant differences in complicated parts of the mold. When we activate actually the cycle 832, we may get some errors exceeding even the allowed geometrical tolerance, which actually here were caused by improper setup of toolpath, namely selection of the cutting tool diameter with respect to the radii of those shape details on the mold. Again, it's something which in reality we would get just on the machine. So here in completely virtual environment, we could have seen already the impact of the process setup. Very important is then the comparison between the predictive and post-process digital twin, which we can see on the pictures here. Our study was performed on a horizontal mid-size machining center with compact design and quite high stiffness. Therefore, we can see that results coming from both the predictive and post-process digital twins are completely the same, with just small differences, confirming that we can use the edge data on the machine for a high reliability of evaluating the machining errors and surface quality. Last but not least is of course important how the virtual results look in comparison with the reality. Here the comparison of the scan of the machined surface with the visualization obtained by the post-process digital twin. Again, we can see a very close distribution of the machining errors and surface quality. This altogether validates the digital twin both in the predictive and post-process form as a reliable tool for predictive testing and post-process evaluation of machining results. And this is actually something which can give us the chance and see the vision about how we can use the digital twins in the concept of distributed production. Let's imagine we have company number one, which is responsible for the complex product and distribution of tasks to more producers. Then we have a company number two, which is equipped with the digital twins of machines in different production sites, and which can run in the manufacturing execution system the virtual simulation and evaluation of the output of single machines which are available at different production sites. And last but not least, then we may have more production sites which are equipped already with the real machines. And after evaluating the results in a virtual environment, the company 2 may already distribute in an informed way which companies will get the manufacturing tasks and which will complete the whole production, then leading back to the company number one, which is responsible for the whole product. So let's see, this might be a vision about how we can use the digital twins in distributed production and how the digital twins may help in scheduling the manufacturing tasks among more manufacturing sites. So this is actually the conclusion of my short talk. I thank you for your attention, and if you have some questions, I will be happy to answer them in the cafe break. So thank you.
Thank you very much. Thank you.